You would think the whole world would be nothing but potato farms.
Run away, run away. Hello and welcome to the Hackaday Podcast. I'm Elliot Williams.
And I'm Al Williams.
This is episode 274. We'll be talking about Capstan robots, avionics of uncertain purpose, and what the frack? This week in the news is no news is good news, so we thought we would take a second to remind you that SuperCon's coming up soon. Well, not soon. It's November 1st through 3rd in sunny Pasadena, California. But we also want to remind you that our call for participation is still running. So I'll throw a link in the show notes to the call for participation forms. If you have a talk or a workshop you want to give, head on over, fill that out. We got slots for long talks, 40 minutes. We got slots for short talks, 20 minutes. If you've got a workshop burning in your brain and want to give it, then definitely apply for that too.
Yeah, somebody asked me the other day what's my favorite event at SuperCon, and of course, naturally, I think it's the soldering competition, but truthfully, it's hard to pick, right? There's just so much good things going on, and even just the social aspect of getting to see all these people that you may or may not know from online, but not in person is really awesome.
Yeah, that's the one. It's the random conversations and talking to people and just hanging out and, oh my God, what are you up to? And with people you know and have known for 10 years and people you just met today. I think it is like that. Those are the best parts for sure.
Not to mention, where else can you say, hey, does anybody have an Arduino? And 5 people will stand up and walk over towards you, right? So
I think you're better off with, does anybody have a soldering iron? Even though we have tons of them.
That too.
Does anybody have a supercapacitor? And people are like, how many farads? You know, it's Arduino. That's shooting fish in a barrel.
This is a journey into sound.
What's that sound?
What's that sound?
Well, then let's head on off to What's That Sound?
All right. Am I allowed to listen to it now?
So you all had a chance to guess last week. Now it's Al's turn. Give it a shot. Yes, now you're allowed to listen.
Oh, something in my brain's telling me something about ascending chromatic scale, but I don't know why that's coming into my head.
It's an F-sharp major chord, but that's not really a good clue at all.
No. It sounds oddly familiar, though. Yeah, all my years of piano lessons as a child have all been long erased, so I think I can find middle C. That's about it. So yeah, that sounds really familiar, but
It does, doesn't it?
Okay, I'm just gonna give up. What's that sound, Elliot?
I'll tell you what, Christina Panos brought this one in, and it is the so-called XDR cassette tone burst. So they put the sound, or toward the end of kind of the cassette era, they started playing the sound at the beginning of a cassette tape, and then they would use it for basically quality control. They'd play it back and see if the cassette was mastered correctly. And I had no idea what it was called. I've definitely heard it. And like you, I had no clue.
Interesting. Why is there not a Hackaday article on this?
If you read the Wikipedia article anyway, they eventually started doing something similar with like a DTMF dual tone system and incorporating data, putting data in the second set of tones. So like different cassettes would have different startup tones, apparently.
Oh, and there were 3 different XDR tones. That was the last one, apparently. 15 sine wave tones, 11 sine wave tones, or the chords of F-sharp sine wave tones.
Yeah, right.
So given your clue, I'm assuming that was the last one.
I think it was the chords of F-sharp one. I'm not 100% sure either. Don't hold me to it. It was Christina's sound.
Wow. Good job, Christina.
Pretty cool. Yeah, I love these ones where you learn something along the way.
So did we get a lot of correct answers?
We didn't. This was a total stumper. We got 22 people wrote in and 7 of them said something right. Actually, more people said it was an audiologist's hearing test type thing, you know, like test tones, frequency range hearing test, audiologist's hearing test tones, calibration device for a sound pressure level meter, not a bad idea. Hearing test or played backwards, you know, how low can you hear? Auditory limbo. Sort of. It's not for testing people's hearing. It's for testing cassette tapes hearing or recording quality. 7 people got it right. So let's see. 7 people, 8-sided die. Here we go.
Are we going to have to start calling you the Dungeon Master, Elliot?
This is from my wife's D&D days, not mine, actually. Oh, and the number's 8, so we throw that one away. We roll it again. A flaw in the system. 7. So congratulations to Ferric Bueler. Oh, nice name. Ferric Bueler, XDR audio test tones found on cassette tapes. Boom.
That would be a great title for a parody of the Iron Man.
Anyone? Bueller? Congratulations, Ferric. We'll get in touch with you, get you a Hackaday Podcast T-Shirt, and everyone else tune in next week for your chance to guess and win.
Do we start playing that tone at the beginning of every podcast now? I think that's a...
Well, my first hack this week is gears are old and busted, capstans are cool. This is kind of an exploratory hack on making a gear reducer for a motor for the legs of a robot dog or a dog-like robot. And this is Aid Musa again. He's made a couple really interesting dog robots and documented them all. And basically, he's trying to do as much with 3D printing as he possibly can. That's led him to do some pretty non-conventional, some pretty interesting gearbox choices in the past. He's done the cycloidal drive, for instance, and he even built one where the cycloidal drive was inside the rotor itself. And so he had a big rotor around the outside of it. And that was really cool. Very flat, honestly. But one of the problems with 3D printed gears is that, 3D printing has layer lines and it's only got so much precision. And the gears wear and they work, but they don't really work for high load applications like, a full on jumping quadruped robot. And that's what he's looking for here. And this video is him documenting his experimenting with Capstan drives. And they are awesome. Basically, you wrap a piece of rope or wire or line around a small pillar, and that's the driving one, and then you wrap it around a bigger pillar. The small pillar is connected to the motor, and the big one is the output. And of course, the different size between the two of them gives you the gear reduction. Cool thing is that the rope doesn't slip around the capstan if you wind it kind of 5 times, and that's due to the capstan equation, which has the friction of the rope around the capstan proportional to the force, but then also proportional to the number of turns. But both of those are in the exponent, and he goes through some of that math in this article. In short, his pulley system isn't going to slip for like thousands and thousands of pounds of load. So it's pretty amazing. The problem with them is that the rope/line is prone to stretching, and that gives you slop in the system, which is sad because otherwise, in principle, with the completely non-stretchy rope line wire, the capstan drive is absolutely zero backlash, which is really important for robots like this. He experiments with a couple different lines, and first I guess he's doing stainless steel, and that fails to flex. And after a few hours of running, just snaps and breaks. You know how metal fatigues? Yeah, it does that when you run it around a really small capstan. He settles on Dyneema DM20, which is a super non-stretchy synthetic fiber. And actually, we've seen that used in place of belts in some 3D printers. I've seen Dyneema used in a couple places. I've also seen it used as a fishing line, I guess, right?
Yeah, PrinterBot was famous for that. Some of their cheaper printers didn't have belts. They had fishing line.
You know, the particular grade of DM20 that he picks is supposed to be the least stretchy thing on the face of the planet. So, pretty cool. He doesn't have 4 legs yet. He's just got 1, but it's capable of jumping up and down on a linear rail. Of course, he tests it to failure, and the thing eventually cracks a hip. But 3D printed plastic hip, just print another one.
Your trivia answer for the day is the Capstan equation, I think, is technically the Euler-Entelwein. Is that right? Entelwein formula, something like that, which is Euler, of course, very famous, but I guess Entelwein was another somewhat famous mathematician. I'm really surprised we don't see more of this. And honestly, outside of the 3D printers, I can't think of when I've seen something like this in ordinary life recently. But it also was kind of reminiscent of me taking apart old radios. If you remember, all the old dials had rope, had little strings, and you'd move the dial and the little pointer would move around. And of course, those were insanely hard to redo. And the rope stretched, like you say, the string would stretch. it wasn't quite the same thing because it was really more interested in the motion than it wasn't like, oh, it was a big force. You're moving some 5-gram pointer across the dial. But yeah, almost all those old radios with the big dials had that sort of arrangement.
I was trying to think of places we see Capstan robots, well, Capstan drives in the real world. And the flagship example of a Capstan robot is the Da Vinci surgical robot. And basically there, you need to actuate these tiny little robot arms that are going to be actually operating on a person. So they need to be packed in pretty tight and they need to be very compact, but also strong. So the motors have to be located, very far away from the things that they're actuating. And that's one of the things that cable drives, anyway, are really good for. And of course, what do you got on the other end of the cable drive? Capstans. Aid's robot here is basically planned after one we saw coming out of Stanford called Stanley for the Capstan drive. They called it Stanley. And I'll throw a link to that right up in the show notes for you. Capstan Drive is pulling the strings on this dynamic quadruped. I love cable-driven robots and skybots and everything else accordingly. So I've got a ton of links to dump on you here, including some people in the comments said, hey, why haven't we seen any 3D printers using this? And we have. We've seen a ton of them. And like you mentioned, one was, which was it?
Printerbot was famous for that years ago.
Darren Schwenke has a crazy one, which is basically a 3D cable printer remixes the Delta. It's a Delta robot with cables. Really interesting. It's got a vertical pull to provide downforce. Otherwise, it's kind of like one of those gondola wall printers, except with 3 things instead of just 2. The craziest 3D printer mechanism I've ever seen is the Marionette printer. Marionette 3D printer replaces linear rails with string. And there, he's just got the print head floating. It's got 6 different lines on it, all of them driven by little capstans. And some of them are even oddly shaped. They're eccentric to make up for differences in geometry and stuff. That's a crazy design. You should absolutely check that out. Last but not least, we have an interesting cable-driven robotic joint, and this was from back in 2020. It was a video by Scientific, and there he's using the cable mechanism to make an elbow-type joint in a robot, and he has the motor up where the shoulder would be. So again, the arm's lightweight and driven with mechanical advantage by using this kind of little capstan, big driven part mechanism. And last but not least, and this comes out of an article that Sonia Vasquez wrote ages ago about cable-driven robots. It's a course given at Stanford, CS 235, Applied Robot Design. It is a lecture on cable transmissions. And if you want to know anything about any of this, including tons of practical hints and tips, you should check that out. And if you're half as interested in cable bots as I am, you absolutely need to watch this class. It's fantastic. He actually suggests using Dyneema in there because of its stretch characteristics. Anyway, definitely check out Aid's video. It is absolutely fantastic. And just his instruction, his presentation, I guess he's in college right now. He should absolutely grow up to be a college professor if he doesn't find a better way to make money. It's just one of the most beautifully explained videos I've seen in a long time.
Kristen, who's a ham radio operator with the ARRL, had Hams Bust the Myth of Ground, and it's actually a talk she gave at the ARRL conference, which is coincident with the Dayton Ham Fest. I think that's really the takeaway from that is we say ground, but we really mean 5 different things when we say ground. So you kind of have to, I've often used that example. If I say, go get me a truck and you bring me a pickup truck and I say, how am I going to transport 10,000 gallons of gasoline in that? Well, because I wanted a tanker truck. And so you got to be a little more specific. It's a very interesting video, but if you really think about it, there's ground for lightning protection, there's ground for zero reference, there's ground for RF shielding, there's, et cetera, et cetera. And I think that's why there's so much confusion on that topic, is if you really don't think about it, you think, well, ground, well, why does it mean this? Well, it doesn't mean that in the context you're thinking about. So she does a pretty nice job of kind of running through all those things with a lot of practical examples, antennas, grounding systems, lightning protection and ESD being kind of similar, just a matter of scale difference. And I just thought it was a really interesting presentation of something we throw around really frequently, but maybe we don't think about it often enough. And where that really bites you is with beginners. So if you've done it long enough, you just kind of normally shift gears and go, oh yeah, we ground it with the copper rod because we need to protect against lightning or what have you. But if you're just starting out, I think that's a major point of confusion. If you forget what it's like to start out, you just have to go teach a class of kids. I remember one time doing a class and we were doing drawings, and I said, now make sure you dimension things. You really want to put the dimensions on things because you got to be able to build it. And I got a lot of drawings that would have like a 4-inch line and the dimension on it would be 4 inches, right? But it was supposed to be a 6-foot piece, at scale. And so you're like, oh, wait, no, the dimension has to be the real dimension, not the. So they would sit and draw the line, measure the line, write the length of the line down. And, that sounds funny, right? But, if you're in the 8th grade, that makes perfect sense. So my fault for not being more explicit. And I think grounding is the same thing. You've been doing this for a long time. You're going to throw around that word, but it does, just like capstan doesn't always mean the same thing. Well, ground doesn't always mean the same thing. And Kristen did a great job of covering that.
The multiple worlds of different grounds kind of usually don't run into each other. Like I'm doing small, low voltage electronic circuits. I don't care about protective earthing, right? Like I'm running this on a lithium ion battery. Ground is the negative terminal on the battery, right? And, it's not in any real sense grounded. And so, yeah, I know what you mean. There's like all these different ideas about, what is it? It's your voltage reference, right? But then it's also a safety ground. And those two aren't always the same, and don't always get used together. But then when you start setting up antennas, all of a sudden they do. And so in the ham radio world, like they kind of clash with each other more than in any other field I've been playing around in.
Yeah, and you've got your ground as a counterpoise, the fake half of the antenna. Anyway, it's a great video. It's not short. I think it's almost an hour's worth of video, but it goes fast and it's a lot of good information.
Well, speaking of radio hacks, the PI Pico, an SDR receiver front end, is a fun hack by Morday. He uses the PI Pico as a direct conversion receiver. Let's see, if you know about radios, usually you have a carrier frequency and then you have some modulation around that. Inside a radio receiver, you then have some kind of a mixer that has a local copy of the carrier frequency, and then you mix them together. The carrier frequency gets subtracted out, and then you have the signal left over. That is not what's going on here. The antenna plugs straight into the PI Pico, and he is sampling that pin as fast as possible. And that means that he's only getting 1 bit out of it, which sounds a little bit weird. He's using the pin as basically a comparator. It's using it as the digital GPIO rather than running it through the ADC, and that's because the ADC is way too slow to do direct conversion. So what he gets out of this then is just basically a stream of ones and zeros, but a stream of ones and zeros at the carrier frequency. So, many, many megahertz instead of kind of audio frequencies. He then is in math XOR mixing these with a local clock inside the Pico. So he's doing the demodulation mixing inside in math after it's been sampled. And I guess that was what makes it truly a direct conversion receiver. It's fun the way he does it because, of course, this has to go on at, full speed, basically. And so he's doing this mixing by, kind of implementing his own XOR function using the PIOs on board. And the fun thing about the PIOs on the Pico is that they run at full clock speed. And he's got this kind of weird jump table-y thing to do the XOR because the PIOs don't have a native XOR to them. Anyway, it's a neat project from the radio side. It's a neat project as a kind of demo of what kind of crazy math things you can do with the Pico's PIOs. At the moment, he sends the output of this to GNU Radio and does some of the demodulation outside. But he says there's no reason he couldn't do it on the chip. He just wanted to get the project finished. And it was the easiest thing to do to pipe it into GNU Radio. But there's a demo video, and he apologizes that it's so noisy, but man, sounds like FM radio to me. So kudos.
It's not amazing that the dog sings well. It's amazing the dog sings at all, or something like that, right? Or maybe it
Right?
was a horse or something. And I think that was my reaction here. What a interesting piece of well, I hate to say it, hackery, right? I mean, because it's not really the best thing to do. I mean, there's no doubt about that. But he overclocked the Pi to get the speed he needed. The 1-bit ADC, if you really look at it, is even weirder than you think because he takes a sample and then outputs it to another pin in the PIO and feeds it back through a resistor to bias the input pin so that he can catch the next sample, right? So it's not even just he feeds it into one pin and just somehow, I guess if you were doing digital, you could do that, right? You could say, okay, I'm going to watch the zero crossings or whatever. But in this case, he's actually feeding signal back in, and he's got a big discussion of the pull up and pull down resistors and how you can turn them both on and get different effects. And I mean, it was really wild. I have no idea what the practical use of it would be, but I was suitably impressed. So I think at the end he's got what, 3 external components and the Pi, and that's it. So maybe it's the crystal radio of the 21st century, I guess, right? Is a Raspberry Pi in 3 parts. The direct conversion receiver part, I mean, that's more or less old hat if you have normal things, right? You just kind of mix down to baseband and go. But being able to do that on a stock Pi with just a little bit of wiring and, like I say, maybe 2 or 3 passive components is super impressive. My next one was, anytime Ken Sheriff has something, I'm always interested. I would say I want to be Ken when I grow up, but I guess it's too late for me to say that. And I think part of that is we have a lot of similar interests. I used to actually take apart chips, and I've worked aerospace, and so a lot of the stuff he does really just kind of reminds me of other days. So this was no exception. He wound up getting an old Mystery Aerospace computer. I think he got it from Usagi Electric, the guy that builds, does a lot of the stuff with the Centurion and the Diskies and all that. And it kind of looked like an Apollo Disky, kind of, sort of, but not exactly. And so they tore it apart and still don't know what it is, but it was just an interesting teardown. And I think what really amazes me, and you'd think I'd be used to it by now, but man, the space stuff has been so high tech for as long as you can remember, because the date codes on that stuff was like from 1967. But as 4-layer PC boards, I don't know about you, when's the last time you saw a 4-layer PC board in 1967? Well, apparently on whatever was using this box, right? Which my guess is some kind of satellite or something. It was so very impressive. And of course, the thing's just jammed full of high-tech ICs for the day. There's also 20 core memory planes, which is a dead giveaway because the core memory is radiation hardened by default. Even the space shuttle, when it first flew, had core memory in it for that reason, because nobody could make reasonable semiconductor memory at that time that was radiation hardened. They finally did, and the shuttle got an upgrade. So it was just fun. I don't know that there's anything practical to it. I mean, most of these teardowns, there's very little practical you take away from them. But wow, what a great box. And then you sit and think, man, people really sat and designed this box, thought hard about it, laid out PC boards in the 60s when that was a manual intensive process. Heaven knows how you debugged something like this with, probably nothing better than an oscilloscope that would be a toy these days, right? And yet here it is, and I guess it's in somebody's junk pile, and now Ken's got it. So I don't know. I think if that had been something I had designed in 1967, which is actually would have been a little early for me, but not by much, I would be happy to see it in the pages of Hackaday and on YouTube, and people looking at it and appreciating its design. So.
Man, it is just such a beautiful piece of electronics, and it's got, like you mentioned, it's high tech for its day. It's got these big boards, and they've all got flat pack chips on them, and there are all these kind of gull-winged out dip-like packages. I don't know if you've seen the flat packs, but that was the original surface mount components basically back in the day, and I think must have been cutting edge back then. I don't know, I wasn't there. The other thing that's stunning about this is the way the different boards all stack up together and fold out in a book. There's kind of this like steel or aluminum frame that holds it all together, and 14 different boards all kind of fold together and over each other into this notebook/cube. It's really just the physical layout of the device, just the mechanical build is really pretty impressive too. But yeah, just a feast for the nerd's eyes.
Yeah, I noticed in the comments a lot of people were speculating it was some sort of avionics for a flight cockpit for something that required a pressure suit to fly. I guess there was some indication it had a port for that. And so that narrows it down. You know, there were just a few of the bombers and spy planes that you had to have a pressure suit to wear. But I don't know. That's outside my wheelhouse. But it sure is a gorgeous layout. And, of course, built like a tank, as you would expect. It's kind of interesting, though. Space technology and aerospace technology, a lot of that has gone the opposite way now. Where in the 60s you were saying, oh, we got to innovate, we have to do better, we've got to get these, high-tech parts that are cost $1 million. But in my lifetime, there's been a big push to go, well, we don't want to do anything new. Let's get the stuff we know works. And so some of these satellites and all that we launch have hardware in them that you would laugh at. Your phone's 20 times more powerful. And we're only now seeing some of the more modern vehicles actually go ahead and say, all right, we do want to get something that doesn't look like it was, a 1970s era microcontroller and some of that's the radiation environment, some of it's the cost for qualifying, but I think some of it is just like I always used to say, nobody got fired in the 70s for buying IBM, right? If you picked up the Honeywell computer that had been on 28 different missions, then there was an assumption it would be okay for the 29th mission. I suspect some of that could be going on here as well, but still, great box, great teardown as always. Always love stuff from Ken.
Well, then my last hack is it's a reverse engineering of some ancient hardware. Old dot matrix displays give up their serial secrets. And this is the story of Michael reverse engineering some Plessey GPD 340 LED displays. And these are really cute. I don't know how old they are, but probably from the 80s. They are little 5x7 LED arrays that are probably about a centimeter tall. There are 2 of them on a chip, and it's an 8-pin chip. And the question is, how do you make these things work? And Michael looks around, can't find any documentation for it, and so decides to have a go at it himself. They look really cool, and it's awesome to get these old parts running again, but I think what I liked most about this and what you could take away from it is kind of the steps he went through to figure out how this thing works. And he started off with a power supply and an ammeter so he wouldn't fry anything basically, and just kind of probed all the pins. And only one combination of the 8 pins gave him basically an 8 milliamp draw on the power supply. And so he reasoned that those must be the power pins. That must be this thing waking up. So he called those VCC and ground, and then he has 6 pins left. And so, he made some educated guesses, like it's got to be probably a serial protocol, given that it doesn't have enough pins to do parallel for any of that, basically. And tried poking around and couldn't get anything going. So finally resorted to brute forcing it. And I love this rig. It's a PI Pico hooked up to all of the 6 different lines, and then a INA 219, which is a current sensing chip hooked up to the power rails. And so he is then trying to send clock and data to one pair of pins on the thing and then keep the other pins in a known state. And doing this for all possible combinations of the 6 pins on the thing. Brute forcing the possible pinouts, basically. And so he lets this thing run, and lo and behold, there are 2 really strong peaks on the current meter, and he can actually see garbage because he doesn't know how to drive these things yet, but he does see lights light up, and so he knows he's on the right track. And just from reading the spikes off the current meter can say, aha, this must be a clock line, this must be a data line, this is a clock line, this is a data line. Once he knows basically which lines they are, figuring out the serial protocol was kind of trial and error and handwork. But I just love the idea of brute forcing a chip and seeing what it does and measuring the current draw to see when it's doing the right thing. And I just thought that was super clever.
Yeah, I was also very impressed. It was funny when I saw the number on them. I said, well, surely there's something out there on the internet. So I Google it and I said, oh, there it is. And I realized, oh no, it's the GitHub that he put together. Oh, duh, you know.
Hey, look at this. Some guy wrote it up. Oh, look, he's covered on Hackaday.
Not my smartest moment. You know, that happens a lot where I look at something and then I go, oh, wait, that was us. We did it. Or a lot of times I did it and I don't even know it. So it's curious. I'm not motivated enough to do it. But now that he knows the protocol, I wonder if these were second source. They looked suspiciously like HP displays to me. And I wondered if maybe they were second source HP with a different number. And you could probably figure that out now that he knows what they actually do. Very impressive, though. It kind of reminded me of the brute force password attack, right? Just try a bunch of passwords till it works, and using the current sensor to figure out, the LEDs are going to draw a carload of current. So that was really smart, and I thought that was fascinating. They are gorgeous looking displays. Reminded me a little bit of the old hex displays like you saw in the Cosmac Elf, although those didn't have all the letters, but they had the hex numbers. Those were parallel devices, though, so pretty smart of him to figure out that was clock and data and the serial protocol and all that. Okay, my last pick of the week was from Allison Marsh over on IEEE Spectrum, and it's a piece looking at the mechanical computer to predict tides that was done by Lord Kelvin. Man, that guy got around, didn't he?
Yeah, right?
I feel like every month I write something and it goes, oh yeah, that works out to be. And of course, he was actually William Thomson, but we've talked about him before with the Pupin coils and the transatlantic cable, and of course everything thermodynamic has got Kelvin all over it. For God's sakes, they named a temperature scale after him. What else do you want? The machine is just beautiful. And I didn't know this much about tides, I'm embarrassed to say, given that I've sailed and I've lived on a beach for a lot of my life. I guess modern science knows that there's hundreds of different rotary motions or whatever that contribute to the tides, but modern machines only use 37 of them because after the 37th one, they don't really make any significant difference. Kelvin's machine only did 10, but that was still awesome at the time, which was 1870, I guess. It's hard to believe, but back then, knowing the tides was actually considered a war secret. So it was all top secret hush-hush if you had tide tables. This was part of why he was able to do this, though, is that they were very interested in measuring tides. And so he had access to tide charts from different places and was able to correlate the data. The thing was really sophisticated. You turned a crank and there was actually a pin. It looks like a strip recorder if you're old enough to remember those. So it's actually drawing on the little piece of paper, the roll of paper, and it would make little marks for the time, and it would make like a special mark for noon, and it was tied to one particular place, right? It wasn't, you couldn't just say, well, I'm just going to set this knob and now I'm looking at this particular area. It was built for one area. But you could actually turn the crank fast enough that you could do a year's worth of tide in 4 hours, which is pretty good. I wonder what a modern tide predicting computer, I'm sure it could do a whole year in less than 4 hours. But on the other hand, this is 1870, pretty cool. But it's interesting progression, too, because I was reading that I guess Newton figured out kind of what was happening with tides in 1687, and it was Laplace was like almost 100 years later that figured out how you could express that as oscillations. But then, so what is that, 1780 or something in that? And it was another 100 years, 1870, before Thomson or Lord Kelvin came up with the machine to actually do that. So I don't know. I guess I'm fascinated with tearing down odd machines. We had Ken's aerospace computer. We've got this machine. The old machines really fascinated me this week, and this one's certainly beautiful.
I'm surprised it needed 10. I'm absolutely shocked that you say there are predictors that use 37 components. 10 components. Like, I'm trying to think of what they could even be. I've got the moon, I've got the sun, I've got, what else drives the tides?
Oddly enough, NOAA, and I'll throw the links in the show notes, I should have put it in the article, NOAA has a description of the formula it actually uses. And so the height of the tide is the output of the equation, and then it has the mean height of water level, the mean amplitude, factor for reducing the mean amplitude, the speed of, so I don't know exactly how all this is done. Yeah, this is something you could dig through and probably figure that out. And of course, it doesn't really get into this, but I don't think Allison's article got into this, but this was one of those ideas whose time had come. So in fact, other people were building similar things at the same time. And William Farrell actually did the first one in the U.S. He was with the U.S. Coast and Geodetic Survey. So that was around the same time, 1882. Yeah. I don't think he was necessarily aware, but he had a different equation, and he didn't do the curves, but he had like scales, and so you had to write down what was on the scales. A little less elegant, perhaps. But then they've got more information about other formulas that have been used by different machines. So perhaps this is the thing that you want to look at if you want to answer that question. It says since 1966, the U.S. has used computers initially programmed in Fortran, so that's kind of interesting. Interactive telephone dial-up access to a UNIVAC computer replaced the CDC and IBM mainframes in 1979, and a Diablo 1640 printer replaced the Wang. That's a daisy wheel, if I'm not mistaken. So I'm just reading off of that page, but wow. So this has been I guess Noah's had a history of computing devices starting in 1965. Pretty cool.
Well, not quite as old as Lord Kelvin's. All right, quick hacks this week. I'll start off with thermoelectric module keeps printer filament cool and dry. And this is a project by Ben Kreschke. It's basically a Peltier cooler to make a dehumidifier for his 3D printing filament storage box. I always joke that Peltier coolers are a major source of hacker tears because they never work as well as you want them to. And he's actually got it working here. Basically, it works like you think. The cold side gets cold, condenses water on it, the water drips out of the system, and that dehumidifies it. Kudos for him for tackling his mountain of surplus Peltier coolers and making it do something useful. John Dyke, the Dyke Delta, a DIY flying wing fits 4, was a really neat tip about an old plane that is a flying wing out of the 1960s, entirely DIY experimental airplane build, and there have been 50 of them built so far. And you could build your own if you have a spare kind of 4,000 to 7,000 hours of labor to put into welding the frame together. Lewis Abbott Glow Blaster uses 405 nanometer laser to make its mark. He basically takes a glow-in-the-dark target and a 405 nanometer laser, which makes this really lovely, long-lasting phosphorescence pattern on them. If you haven't played around with the kind of blue lasers and glow-in-the-dark stuff, you really owe it to yourself. It's lovely. He throws in tactile feedback and a pew-pew sound generation to this thing to make it feel like a real laser gun, and it looks super fun. And last up, gamma ray spectroscopy the Pomelo way is a demo of the Pomelo scintillation counter that Mihai Kuchik has made here. It's really neat. It uses a very small scintillation crystal and a silicon photomultiplier instead of the old kind of vacuum tubey ones, and that means it runs on a much lower voltage. It's probably a little bit less efficient, but this lets him characterize radioactive samples by the different strengths of gamma rays they give off.
Very cool. My first quick hack for the week, the Radio Mechanic, old knobs with a cast of thousands. You've got a knob that needs to be replaced. It's on some piece of old gear. Sure, you could 3D print it, but really FDM printing's not going to look great. You can resin print it. I'll be honest with you, I've gotten to where I hate resin printing. What he does is he takes the knob, one of the knobs off the radio, and casts it in silicone. And he does have some nice 3D printed jigs that looked very nice for holding the knob in the right place and getting the mold set up. And then, of course, he casts it in some sort of resin. Really nice. He had a few problems with it not being as translucent as he liked and had a few air bubble problems. A lot of people in the comments trying to help with that. I think the only problem I saw with it is it looked super labor intensive. Whereas, if I needed 143 knobs, I can go print those probably on one bed or maybe 2 or 3 runs of a resin printer. Doing 143 casting operations would be a bit of a pain, right? Second up, from Oscar 2517 was VFD tube calculator shows off wide array of skills. I don't know. It was just something about it piqued my interest. The VFD tubes they look great. They look like Nixies, but they're a lot easier to mess with. The whole thing from the laser cut box with the wood look on it, I think it was like probably contact paper or veneer. It just reminded me of something you'd see like in a 1973 Electronics Illustrated magazine or something. And I just thought it was a cool project. And then from the things we always think we're going to do but never get around to it department, Martin Brahm has TurboCase, which generates a PCB shell for you. You know, one of the things you justify in your mind for having a 3D printer is, oh, well, when I need a case for a project, I'll just 3D print it. This thing is a open SCAD script that will generate little boxes for you that you can use for projects. And it's got a lot of nice features. You get to tell it what you want, and the box pops out. And then presumably you go print it, and then you've got a box. So it's one of those things you always think you're going to do. Martin did it, and we thank him.
And that brings us to our Can't Miss articles. These are long-form pieces written by our lovely Hackaday staff. And this week I started off with the ever-lovely Al Williams's Tech in Plain Sight Theodolites. Is that how you pronounce that?
I hope so, because that's how I always say it. And who knows? I'm not a civil engineer. They may all be snickering at me every time I say it.
I've never even heard of a theodolite, but I've absolutely seen them before. These are those things that surveyors have around on tripods, and I've always wondered what exactly it is they're doing, and this article told me, so thanks, Al. And actually, if you see surveyors out in the field these days, they may be using a slightly more fancy piece of equipment called a total station, but that's just a combination theodolite and rangefinder. A theodolite is, and correct me if I'm wrong here, is basically just kind of an angle measurer. And so you're trying to triangulate one position based on two other known positions. And that's how surveyors figure out where a spot is. True?
Yeah, it's a very, very precise angle measurement in all dimensions. So it's got to be really level. It's got to be, you got to know exactly where it's over. I mean, a sextant measures angles, right? But that's not going to get you the precision you get with one of these instruments.
And it's really interesting. You were going through some of the earliest designs of these and pointing out that the limiting factor was figuring out, precisely how many degrees or arc seconds or fractions of an arc second or fractions of a, or micro radians a thing has turned. And that's really interesting. And I never thought of dividing a circle into so many different segments as being an impossible problem. But of course it is. And if you think about how to do it yourself, and how to make a machine that can make things to do this accurately, it's actually really hard. And so you mentioned briefly in this article that, Jonathan Sisson's 1725 dividing mechanism here is what made these work. And I would love to see one of those things work. Maybe that's another Tech in Plain Sight.
Yeah, and that's tightly related to screw cutting lathes too. A lot of those guys were also into that. And I think we did do a piece on that one time, or at least tangentially. But yeah, it's amazing. And that was the technology step there, was being able to figure out how to make nice even marks around a circle at high precision. Because if you don't have the precision there, who cares?
If you think about trying to figure out where you are based on two other landmarks, you can look at the angular difference between the two and then the distance to the two known landmarks. And that kind of gives you the triangle you need to figure out exactly where you are. That distance measuring part, like sometimes you see surveyors doing it with like chains and stakes, but then these total stations must have like a laser rangefinder or something in them these days, right?
Well, it's interesting, too, that they did use these also for tracking altitude of early rockets. So that's another case where your angle measurement is really precise.
I'm going to have to mention what I think is the most gonzo work of surveying ever was Eratosthenes. So he wanted to measure the circumference of the Earth. He dug two pits of known depth in two different cities. Since they were on the same meridian, he could use the length of the shadows inside them to back out the diameter of the Earth. The trick is, how do you know how far away these two cities are back in ancient Greece? And the answer, and this is absolutely insane to me, the answer is they hired people called bematists who had known consistent paces. And they actually had some dude walk from Alexandria to Syene which is, how far away is that? No, it can't be 600 kilometers. How far is that? 5,000 stadia. Oh my God. He had him walk about 800 kilometers? That's insane.
I think you're making all this up, Elliot. I don't believe any of this.
I'm going to put a link into the show notes. It's absolutely, absolutely crazy.
This is like ChatGPT hallucinating, I think.
It is. And the most amazing thing is that he got within kind of 1% plus or minus of the actual radius of the Earth by having some dude pace it out and measuring angles of shadows in a hole in ancient Greece. Makes me feel real dumb.
Yeah, even after you've told me, I can't figure out the math to do that. So yeah, I'm not gonna. Well, you mentioned you didn't know what these were called, and I think it's interesting. For a large part of my life, I always thought these were called transits. But like I mentioned in the article, a transit is a particular type of these, and in fact, almost all of them you see today are in fact transits, and it's really a transit theodolite. But I think once you go to engineering school, you eventually hear somebody use that term, or I guess if you're a civil engineer, you learn it in school. But I think the large part of the population, that's a transit, right? Or at least that's what I always thought it was. So, but I do like the Tech in Plain Sight series because I think it's a chance to kind of look at some of these things that, if you're not in this business, what do you know about any of this? And it's just interesting to see how much thought and science and engineering goes into some of the most mundane things that you don't think about.
I could not put that better myself.
Well, speaking of everyday things that you don't think about, my pick this week was Dan Maloney's part of his mining and refining series, and this one's on fracking. That's a controversial topic, but I think part of it is I'm always fascinated by the idea that we use so much of so many different things. So like all this oil and stuff that comes from the oil and gas and all this stuff, we use an enormous amount of it, and all of it has to be taken out of the ground, moved to different places, made into products, shipped to where we get it from, and you just drive up to the gas station and get gas, right? Enough so that like if you ever go after a hurricane and you can't do that, it's shocking and frightening. And I was so taken by Dan's treatment of that whole industry because there's a lot of things in there, that are kind of unspoken, like the directional drilling is a big thing because people want to go steal oil from places where they're not, right? I drill my hole here, but there's oil over there that way. So let's drill over that way, even though we don't own that oil. Things like who knew? And I feel bad. I live in Houston where this is a big industry. I've had some tangential relationship to the energy industry different times in my life, but I had no idea that one of the things they do is use a mud engine to turn the drill. So there was just a lot of little small things like that I really found interesting in there. Of course, the fracking part of it is trying to induce more product to come out of the shale fields. And while it's been really great, when I was a kid, everybody was, in 20 years, we'll be out of all this. There won't be any more. And everybody will be, very sad. And of course, here we are 40 or 50 more years after that. And of course, people are still saying that, and they may or may not be right. But the fact is, we find different ways to get more out. So this fracking is one of them. But of course, it's very controversial because if you look, people who live near this type of stuff don't think it's, good for their water and good for their living conditions. So it's kind of a controversial thing. The level of odd detail in here, though, it really made it worth the read. So part of what they use to make the gel that they want to use is Guar gum, which is something you see all the time in food products, right? So it's just weird to think who's using Guar gum. Well, the people who make, this food product, and also the people fracking oil and gas out of the ground. This is another one of those things where my guess is nobody listening to us today will ever have to go frack petroleum products out of the ground. Or if they are, they already know about this, because that's their business. But the chances that we're going to have the apocalypse and then all the Hackaday readers are going to get together and figure out how to bring the petroleum business back up is pretty small. But it's just so fascinating that something that's such a big part of our life, we know so little about how it actually is taken out of the ground, moved different places, processed, moved to retail, and distributed. And it's surprising. I remember a while back I think it may have been the first Tech in Plain Sight I ever did, was how the gas pumps know when to stop. And that's one of those things where how many times have you pumped gas? And when the gas tank gets full, it stops. Why? Because there's a little hole in the gas pump and some really smart air flow engineering, basically, that makes it stop. So it doesn't take a computer, it doesn't take a pressure sensor, it's an air hole. So it's the same thing here. How many times have you used stuff that's fracked out of the ground, even heard about fracking on the news, and yet I'll guarantee you, unless you're in this business, if you read this, you'll learn at least 3 things that you didn't know before you read it.
When you hear about fracking, you always hear about the, pumping fluid down and getting it back out and the possible risk to leaching in the groundwater. I had no idea that the fracturing part of fracking was actually done by lowering shaped charges down the borehole and like shooting them off underground.
I was disappointed Dan didn't find a way to put a Battlestar Galactica joke in here, though.
But people in the comments did. Never fear. That wraps it up for this week's Hackaday Podcast. Thanks very much for listening. To see the links and leave comments, head on over to hackaday.com/podcast. And if you see anything cool or do anything cool, send us a line, tips@hackaday.com. And until next week,
Keep those hacks coming.
hello and welcome to What is this?
My speakers here. I was good. I didn't have them set to my speakers. Okay, we've certainly beat that one to death, Elliot.
What did he call them? I can't remember. Damn it. And you're saying that it says that one, yeah. So, I can't say anything smart about fracking at all.
Okay, and true to form, I did lose my window, but I figured out how to get it back, I think. Well,
Jinx.
I've got to stop doing this. I got it, yay.